In the previous part of the lecture, we discussed about how to estimate population parameters, in particular the population mean, using our sample statistics and within a certain confidence interval. Now, how about to estimate the population proportion? So, knowing the proportion of a population having a certain, for example, if you remember back in the lectures on probability, about say you have a desired outcome and undesired outcome, you want to know the probability of getting a desired outcome provided a number of trials. This time we want to know the proportion of a population of our, for example, a desired outcome. What is the proportion, or how much percent, how many of the population has our desired outcome? So it's not a probability, but rather a description of the population parameter, which is the proportion of our desired outcome. But generally, the approach is somewhat similar to the population probability of getting a desired outcome in population, and applied with a confidence interval that we have been talking about in this lecture. Now, usually we do this using large samples. So we have here a confidence interval for the population proportion designated as P. So for large samples at a certain percentage confidence interval for the population proportion, P is defined as your population proportion as your P hook plus minus ZSP. So this is our margin of error. So our value of Z is from the standard normal distribution table, because again, this is a large sample. And for a certain confidence level given by 1 minus alpha percent. Our ZSPs, this is our margin of error or maximum error of estimate. And our S hook P, this is the marginalized standard a standard distribution, which is PQ. Marginalized standard deviation, which is PQ over N. So let's have an example. So in a September 24, 2019 article on newsgallup.com mentioned that according to the Gallup research about climate change issues, 51% of American adults can be classified as concerned believers, meaning they are highly worried about global warming, think it will pose a serious threat in their lifetime, believe it's the result of human activity, and think news reports about it are accurate or underestimate the problem. So, assuming that this poll is based on a random sample of 1,600 US adults, so what's the point estimate of the population proportion? And let's find within a 99% confidence interval, or rather confidence level, the percentage of all American adults who will say that having basic needs met is very or extremely important in their vision of the American dream. So, what's the margin of error for this estimate? So, basically, this is get up not about a probability of finding a person within that population having a certain um, concerns, but rather which percent of the population is a concerned believer. So let's first define what are our terms. So we have a sample size of 1,600, and our desired outcome is the concerned believer. So we have 0.51. So let's assign it as the proportion. This is from the sample proportion from the 1,600 people. That's 51%, so or 0.51. And of course, the other outcome, the undesired outcome, is 1 minus 0.51, which is 0.49. Now, our standard deviation, normalized standard deviation, is the square root of PQ over N. So this is equal to 0.0124975. Now, going back to our probability, we must have a requirement here that NP and NQ must both be greater than 5. This is from the calculation of probability for the desired outcome, binomial distribution, if you remember. So you have here both NP and NQ, they are greater than 5, so we can proceed. Now, the point estimate is 0.51. So again, like the our sample statistic, or the point estimate using sample statistics from the previous lectures. So the point estimate is the sample estimate of the population of 0.51. So you want a confidence level of 99% or 0.99. So how do we know the z-value of that? So again, this is plus minus the point estimate. So that's a two-tailed test. So our alpha, this is 1 minus alpha. Therefore, our alpha is 1 minus 0.99 or 0.01 divided by 2, that's 0.05. So let's look for the value of z that will give us about 0.005 area beneath the curve. So that value is 2.58. When I say area beneath the curve, this is at the extreme ends, leftmost or rightmost part. And then we plug it in our equation. So p bar plus minus z s p. So just substitute the terms. So z is 2.58, our s is 0.0124975. So this is 0.51 plus minus 0.032. So our margin of error, or rather our estimate of the population proportion of our desired outcome, which are the concerned believer, is that the percentage of the population ranges from 47.8% to 54.8%, and that is within a 99% confidence interval. So our margin of error here is this term, ZSP. So 2.58 times SP, this is plus minus 3.2%. So from this data, we can estimate it within plus minus 3.2 or within a range of 6.4%, that the population proportion of the concerned believer is within plus minus 3.2% of our statistical or our sample estimate of 51%. Or rather, it's 47.8 to 54.2%. So that's how you estimate your confidence level. So it's different from getting probability, because we just want to know, if we ask a person the probability of saying yes or no in our question, that is the probability that we have been discussing from the previous lectures. But this one, we want to know the parameter of the whole population itself. So this is a bit different approach, or rather the question is different because it's not a probability of the answer of the person that we will ask, but rather for the whole population, the proportion of the whole population that answers yes or no to our question is what we are actually estimating here. Now, how do we know? This is one of the most common, or the first question, and one of the most common mistakes that we usually do, especially when we do research, is that most of the time, how do we know what our sample size is in order to properly estimate the population parameter within a certain confidence interval? So we do not randomly assign number of samples just because it's convenient. I'll just get 30 samples because it's convenient for me. I'll just get 5 samples because that's only the amount that we have available. So it's not. There is a certain value, minimum value of the sample size, so that we can properly estimate the population parameter. And this is how we do it. So given a confidence level and the values of P and Q, the sample size that will produce a predetermined maximum error, a maximum of error E in the confidence interval estimate of P, this is our sample size, provided that we have P and Q. So let's say we do not know the proportion of the parameters of a certain value. So the first one is get the most conservative estimate. So let's just assume that's a 50-50 proportion of desired versus undesired outcome. And then take a preliminary sample of any arbitrarily determined size and calculate P and Q from the samples. And then from this, we can use to find the value of N. And basically, this is just what is usually done. Or because we do not really know, when we start a study, we don't really know at the start what would be the estimated P and Q parameter. We will only find it out when we do sampling. And since we do not have P and Q values, this calculation would be moot, because basically useless, because we don't have these values. So the first one is, of course, assume 0.5 and 0.5, and then calculate our N from 0.5 P and Q values. So that's what it is. So let's have this example. Lombard Electronics Company has just installed a new machine that makes part that is used in clocks. The company wants to estimate the proportion of these parts produced by this machine that are defective. The company manager wants this estimate to be within 0.02 of the population proportion, that's our E, for a 95% confidence level. So what is the most conservative estimate of the sample size that will limit the maximum error to within 0.02 of the population proportion? So we do not know exactly what's the proportion between a defective and an undefective product. So we will of course use a conservative estimate of 0.5. So assign 0.5 for usable and a defective as 0.5, and so we get our plug it in our equation. Now for the z value, that is based on our 95% confidence level. So this is plus minus. So again, a two-tailed approach. So this is 1 minus alpha percent. So 1 minus alpha is equal to 0.95. Therefore, our alpha is 0.05. Divided into 2, we get 0.025. And that would be the area beneath the leftmost tail and the rightmost tail. So we will just find it and get the value of z from that. So look at the table. So what is the value of the z that will give us 0.025 area beneath the leftmost curve, and also look at the counterpart on the rightmost curve. And then we just and that value is 1.96, and then we just get plug it in our equation. So z squared times 0.5 times 0.5, and our margin of error is 0.02. So this is our error at the bottom. So 0.02 squared. So we need to get 2,400 samples, a sample parts of 2,400 samples. So if the company takes a sample of 2,400 parts, there's a 95% chance that the estimate of P will be within 0.02 of the population proportion. So how about let's do this example. Now again, this amount is very, very large, and it's actually quite difficult. So what should be done? So let's first try. Let's try a preliminary sample of 200 parts. So this is arbitrarily assigned. So it's more convenient. There is no actual calculation here. So let's have it for convenience. Let's just sample 200. So they sampled 200 and they showed that 7% of them are defective. Because again, this is for calculation of defective machine parts, and really an estimate of 50-50 defective means that you are really inefficient in making that, and that's not really a very realistic approach. So they just rather than getting this 2,400, because that's too much of sample parts to sacrifice to testing, they just get 200 parts, which is a more conservative number and more cost effective. And then they sampled it with defective percentage of defective parts. 7% of them were found to be defective. So how large then should a sample be so that 95% confidence interval, that's still within 0.02% margin of error. So same problem, we want to know how much is a sample so that we can properly estimate the proportion. So we are just looking here, we still do not know the actual proportion, and that 7%, we cannot use this as an estimate of the population proportion. This is the sample parameter proportion from 200 parts, and that value of n is still small enough, actually too small, to actually say that we can properly estimate the population parameter from this sample of 200. We are still trying to know here what should be the proper sample parameter, or number of samples, or sample size that we are going to use to actually estimate the sample statistic that we will be using to estimate the population parameter. So this is just like a preliminary sample. So just getting here the sample sizes. So from these preliminary sample, we get a probability of 0.07p, and another is 0.93. So we get z squared. So again, 95% confidence, so this is 1.96, and our margin of error is 0.02 plus minus within 0.02 error of our estimates. So we have, plug it in our equation, we get a sample size of 626. And this is much smaller than the previous one when we did a 50-50 chances of 2,400. So that's why most statisticians, they first do a preliminary sample. For example, when we want to know a certain proportion of a population, we have no prior idea what is the actual proportion. We have no idea what would be the proportion is we are basically starting from zero. That is why the most common approach that we would have is sample as a preliminary sample, arbitrarily assign a value, say 30 to 100, and then look for us an idea of what would be the proportion of a certain outcome that we are looking for. But we will not be using that to actually estimate the population parameter. Are just going to use that to estimate what would be so that we will get an idea what would be the sample size, the actual sample size for the actual sample proportion that we will be using as the sample statistic or the point estimate for our population estimation of the population proportion. So this is the usual approach actually. And then again, using this approach will give us a generally smaller amount of samples than the actual 1,400 that we would have to use. And that's it for estimating within a certain confidence interval the population means and the population parameters.